Okay, so the first speaker is Professor Scott Baden from UCSD. He's working on, in general, I think, on algorithms for high-performance computing. We'll talk about coping with technological change. I guess that mainly involves multi-core. That's one of the things it involves. And just a reminder, you have to stand here talking to the microphone because all these talks are videotaped. So there will be a special YouTube channel for FEniCS where you can find all these talks later. And also download this movie.
Okay.
So stand close to...
If I could change the slides.
Yeah, so I'll do that.
Okay.
So stand close to the microphone and...
Okay, how's that?
So, this, and then you have your...
It's on the desktop.
This one here?
No, it was on the right on. There's a PDF and there should be a PowerPoint. Maybe it's under this window here.
Someone else.
Here it is down here.
How to change to full screen on the Mac?
There should be a little icon just down here. Thank you very much. It's nice to be here again.
Yeah.
The last time I spoke, it was melting heat here, and I'm glad to say I actually prefer it this way. Today I'm going to talk a bit about software activities in my research group, and actually really a retrospective over the years that I've worked in the area. What I wanted to really impress upon you, and I see this is displaying a little bit differently than I had it, is the phenomena of technological change as I've seen it during my professional career. The first machine I used actually was a Cray 1, although not when it came out in 1976, but only a few years later in the early 80s. That machine had a peak speed of 240 megaflops. Today, the highest end systems that we can obtain here, these mainframes, which are today now are over a petaflop, are 7 orders of magnitude more powerful than the original machines that we used. Excuse me. Today it's possible actually to get a teraflop on a chip. That is peak speed. For example, the Tesla machine in which 4 chips contribute to a total performance of 4 teraflops. Now, as we see actually, of course, your mileage will vary and the actual performance might not be quite so high, but it is possible to get enormous performance, much greater than one would have found on the highest end machine 35 years ago. Now, the main influence of technology is that we can derive increased knowledge from more useful simulations that are more accurate, have higher fidelity, and so on. And of course, the development of new algorithms has contributed to this, certainly. But from an architect's perspective, there's been a tremendous change. For example, the emergence of parallel computers in the late 80s and their use more widespread in the early 90s, early to mid 90s, enabled us to do 3-dimensional simulations, whereas before 2-dimensional was more or less what many of us were restricted to. But there's also another very important change. This is not necessarily the one that we always want to talk about, but it's why I continue to do research in this area, is that it also leads to changes in the common wisdom for how to write a highly efficient, well-tuned program. Right? So if we had a magic compiler that took original code and we could continue to obtain performance we wanted, we wouldn't have to think about that problem. But unfortunately, it's an inconvenient fact, and I don't really see it as ever changing. So again, you start from the Cray 1 in 1976 at 240 megaflops. And today you can get a teraflop on a chip. You can also buy a consumer item, a toy, a PlayStation, which will give you 150 gigaflops. Just a very simple toy. And these things are at a price that an ordinary or reasonable user could come up with and purchase and be very happy to use. Right? Now, what I'll talk about then is the enabling technology, a little bit more about the multi-core processor, some performance and implementation issues, and then a cross-cutting issue, which I'll illustrate with a metaphor, involving the tolerance of latency, that is, the delays that are inevitable when moving across large space and time scales, and then a technique for hiding it. Okay? So of course, a multi-core computer is something that we've all begun to learn about, and it explains, for example, why we have seen at UCSD a sudden resurgence in the interest in parallel computation, with enormous enrollments that are unprecedented in our history of teaching parallel computing at UCSD for 20 years. And this, of course, is occurring at other universities as well around the world. But in addition to getting an all-on-chip computer, you also have another liability, really, which is the amount of memory for each core has reduced. This is simply part of the fact of life of how these machines are packaged. We can fit so much memory on the chip, the processors can be fit as well, but as we grow the number of processors, it tends to increase more quickly than the amount of memory. Okay? And of course, in a few years, and you could begin to even say today, that just about anyone will have an unprecedented amount of parallelism, a phenomenon which is new to the field and is creating this interest. In fact, some users won't even know they're using one. Their goal is to simply see a machine that runs faster. And those users used to depend on the clock speed simply going up, and that's how they got more performance. But we know that isn't true anymore, at least not now, until the technology makes some change. We have to use more parallelism instead of going for a faster clock. The other phenomena is that users will not necessarily be from the HPC world. And this is something that those of us who've taught parallel processing have begun to reckon with as our students now begin to look for other opportunities, not just in high performance computing, but in areas such as data mining and so on. In addition, the idea of having to learn in parallel from the start is important, because if students are now learning this field from a very early stage in their careers, when we teach them how to program, there's this sense in which we should be able to bring this into the initial part of their education. Right? What I see in the future, and I think what many of us do, is that the desktops will replace small clusters. And for example, we looked at the picture earlier. Right? Here is a desktop. This is a Tesla you can buy today, 4 teraflops. Here is a picture of one of the early Beowulf clusters, which takes up a rack in a machine room, requires special cooling and power and so on. In addition, the clusters that we see today or have been seeing will have on the order of 1,000 cores in a very small footprint in just a few years. And of course, mainframes will have hundreds to thousands to millions of cores, millions maybe in the coming decade. But certainly in a couple of years, there'll be a machine located in the United States that has a couple of 100,000 cores at NCSA, the so-called Blue Waters machine. And those machines will be appearing elsewhere as well, here in Scandinavia and so on. Now, the interesting part about the component of all these machines, the multi-core processor, is the technology hasn't really settled. At this time, it's exciting, but there's also an element of risk, part of excitement, because it could be in a few years that machines could look very different than we expect they will be today. So the machine on the right is a picture of the NVIDIA chip, which contains hundreds of processors. Each one of those little tiny green squares is one core. There are 240 of them. In addition, we have a processor like Cell, which contains 8 very high-speed streaming cores that are specialized to do high-performance floating point. On the left, a mythical machine which conjured up from the idea that maybe machines will have locality domains. That is, some things will be further away than others in terms of the amount of time it takes to get that data, and this might be hierarchical. We don't really know. Okay? So, and the other idea is that we will have hybrid processors. So we can have a processor like the Cell, which is in the middle, where we have a traditional core attached to these 8 very high-speed cores, or a system such as Tesla, this one here, which contains some number of the amount the user wishes to pay for, of high-speed cores attached to more conventional processors, multi-core processors in their own right, but more general purpose. Right? And there's a sense in which it's possible to optimize power and cost by using a mix of cores in order to have them each do what they're best at and avoid having them run in a mode where they're less efficient. Right? That's the topic of a PhD student of mine working here with people at Simula, Dina Munat, and funded by Simula, to look at this interesting area of research. Okay, where do we sit then?